All right, welcome to our introduction to polynomial functions and graphing. Today we're going to learn how we decide the degree of a polynomial with a variable, how do we determine the end behavior of a polynomial function, along with a number of other ideas. A polynomial function is the function of the form f of x equals a n x to the n plus a n minus 1 x to the n minus 1 plus until you come to a1x plus a0. Okay? All of these a's are coefficients that are real numbers, and the n must be a positive integer. Remember, integers are -2, -1, 0, 1, 2, no decimals or fractions. So positive integers would be 0, 1, 2. The degree of one variable polynomial is the largest power on any x term in the polynomial. Let's take a look at this. A constant function, where f of x equals c, where c is not equal to 0, is a polynomial function of degree 0, and our example is y equals 2. So all horizontal lines have a degree of 0. A linear function, f of x equals mx plus b, where the slope cannot be 0, is a polynomial function of degree 1. An example of this would be y equals 3x plus 1, which you know is the equation of a line. A quadratic function, f of x equals ax squared plus bx plus c, where a does not equal 0, is a polynomial function of degree 2. Example, y equals 2x squared minus 3x plus 5. You study quadratic functions extensively in Math 2. The function is written in descending order of power. Terms with the highest degree determines the degree of the function. Let's take a look at that. Determine which of the following are polynomial functions. If the function is a polynomial, state its degree. Let's take a look at f of x equals 2x to the fourth minus x. Which degree is this polynomial function? That's right. This is a polynomial of degree 4. Let's take a look at g of x equals 2. We can write n an x to the 0. And remember, anytime you have an exponent to the 0, this means it equals 1. So this is a polynomial of degree 0. What about h of x equals 2x to the square root plus 1? Is this a polynomial? No, it's not a polynomial because of the square root, since the power is not an integer. What about f of x equals 3 over x plus x squared? Is this a polynomial? Not a polynomial because of the x in the denominator. The power is negative. It's x to the -1. Which of the following are polynomial functions? F of x equals x to the fourth minus -2 plus 2x minus 9. Is this a polynomial function? No, this is not a polynomial function because you have a -2 exponent. What about f of x equals 5x to the fifth plus x to the fourth minus 2 times the square root of x plus 5? Is this a polynomial function? No, this is not a polynomial function because we have a square root of x, which is a fraction. What about f of x equals 3x cubed plus 2x squared plus 1? Is this a polynomial function? Yes, this is a polynomial function. What about f of x equals 2x to the fourth in parentheses x minus 2 and x plus 3? Is this a polynomial function? Yes, this is also a polynomial function. What is the degree of the following functions? What is the degree of this function here? The 4x cubed squared minus 2x plus 2. That's right, it has a degree of 2. What is the degree of the f of x equals 2x cubed plus 4x to the fourth plus x minus 2? That's right, it has a degree of 4. What about x minus 2x squared plus 3 to the x cubed? What is that degree? That's right, it's a degree of 3. The leading coefficient. The polynomial function has a leading coefficient. Once the function is written in descending order of degree, the leading coefficient is the coefficient of the term with the highest degree. So we have y equals 3x to the fifth minus 4x cubed minus 2x plus 6. What is the leading coefficient? That's right, the leading coefficient is 3. Find the leading coefficient and the degree of each polynomial. We have f of x equals negative 2x to the fifth plus 3x cubed minus 5x plus 1. What is our leading coefficient and degree? That's right, negative 2 is our leading coefficient and our degree is 5. What about f of x equals x cubed plus 6x squared minus x plus 7? What is our leading coefficient and what is our degree? That's right, our leading coefficient is 1 and our degree is 3. X-intercepts. Where a graph crosses the x-axis, you know it is called an x-intercept. But there are two more words used to describe the x-intercept. We have root of a polynomial and the zeros of a polynomial. But all three of these are where the graph crosses the x-axis. Graphs of polynomials are smooth and continuous. No sharp corners or cusps. No gaps or holes can be drawn without lifting the pencil from the paper. Okay, so our first one, this is a graph of a polynomial. It's smooth. Sharp corners or cusps. We have a gap and we have a hole. So this is not the graph of a polynomial. Let's look at the graph f of x equals xn, where n is an even integer. Remember, what are your even integers? They would be 2, 4, 6, 8. That's correct. So we have three graphs here, x squared, x to the fourth, and x to the sixth. Notice each graph looks similar to x squared, but is wider and flatter near the origin between -1 and 1, and grows steeper on either side. The higher the power, the flatter and the steeper the curve. Let's look at the graph f of x equals xn, where n is an odd integer, like 1, 3, 5, 7. Okay, so we have x cubed, x to the fifth, x to the seventh. Notice each graph looks similar to x cubed, but is wider and flatter near the origin between -1 and 1, and grows steeper on either side. The higher the power, the flatter and the steeper the curve. Let's look at the graph f of x equals negative x to the fourth plus 2. Notice it reflects around the x-axis. It looks like the x squared, but wider near the origin and steeper after 1 and before -1. Translates up 2. So this is what our graph would look like. So long as the function is a transformation of x to the n, we can graph it. But what if it's not? We'll learn some techniques to help us determine what the graph looks like in the next slides. Left and right hand behavior of a graph. The degree of the polynomial along with the sign of the leading coefficient of the term with the highest power will tell us about the left and right hand behavior of the graph. Even polynomials rise on both the left and right hand sides of the graph, like x squared, your quadratic, if the coefficient is positive. The additional terms may cause the graph to have some turns near the center, but will always have the same left and right hand behavior determined by the highest powered term. The left hand behavior rises, the right hand behavior rises. Even degree polynomials fall on both the left side and the right-hand sides of the graph, like negative x squared, if the coefficient is negative. Left-hand behavior falls, right-hand behavior falls. Turning points in the middle. Odd degree polynomials fall on the left and rise on the right. hand sides of the graph like x cubed if the coefficient is positive. So the left-hand behavior falls, right-hand behavior rises, the turning points are in the middle. Odd degree polynomials rise on the left and fall on the right sides of the graph like x cubed if the coefficient is negative. Left-hand behavior rises, right-hand behavior falls, turning points in the middle. A polynomial of degree n can have at most n minus 1 turning points. So whatever the degree is, subtract 1 to get the most times the graph can turn. This doesn't mean it has that many turning points, but that's the most it can have. Let's determine left and right hand behavior for the graph of the function x to the fourth minus 3x cubed minus 15x squared plus 19x plus 30. Degree is 4, which is even, and the coefficient is positive, so the graph will look like x squared looks off to the left and off to the right. Okay, the graph can have at most 3 turning points. How do we determine what it looks like near the middle? We're going to find the x and y intercepts would be useful, and we know how to find those. To find the y-intercept, we put 0 in for the x. Notice how we have 30 is left over, so 30 is your y-intercept. To find the x-intercepts, we put in 0 for the y. Notice that x equals 5, 2, negative 1, and negative 3. The signs are opposite of what is in the parentheses. Finally, we need a smooth curve through the intercepts that has the correct left and right hand behavior. To pass through these points, it will have 3 turns, one less than the degree, so that's okay. And notice that we have 3 turns, a minimum, a maximum, and then another minimum. We found the x-intercept by putting 0 in for the f of x or y. They are the same thing, remember. So we call the x-intercepts the zeros of the polynomial since that is where y equals 0. These are also called the roots of the polynomial. Okay, can you find the zeros of this polynomial? There are repeated factors, like x minus 1 is to the third power, so it is repeated 3 times. If we set this equal to 0 and solve, we get 1. We say that 1 is the 0 or the multiplicity of 3, since it shows up as a factor 3 times. What are the other zeros and their multiplicities? Okay, negative 2 is a 0 of the multiplicity of 2 because it's squared, and 3 is a 0 of multiplicity 1. So multiplicity means that your 0 or your root or your x-intercept is being repeated more than once. So knowing the zeros of a polynomial, we can plot them on the graph. If we know the multiplicity of the 0, it tells us whether the graph crosses the x-axis at this point, odd multiple crosses, or whether it just touches the axis and turns and heads back the other way. Even multiplicities touch. Let's try to graph negative x minus 1 to the x plus 2 squared. What would the left and right hand behavior be? In other words, do you have an odd or even polynomial? You don't need to multiply this out, but figure out what is the highest power on an x. Highest power of the x would be if multiplied out. In this case, it would be x cubed. Notice the negative in front. Remember, the negative is going to reflect the x cubed around the origin. Okay, so that means that the left-hand behavior will be up and the right-hand behavior will be down. What would the y-intercept be? Let's put in zeros, and if you put in the zeros, you'll see that you get 4. Find the zeros and their multiplicities. Well, what is the zeros? Zeros are 1 and negative 2, and the negative 2 has a multiplicity of 2, so it touches at negative 2. So this is what the graph is going to look like. Okay? Again, the negative 2 is a multiplicity of 2, so it's going to touch at negative 2. And the 1 has a multiplicity of 1, so it crosses the axis at 1. Steps for graphing a polynomial. Determine the left and right-hand behavior by looking at the highest power on x and sign at that term. Determine the maximum number of terms in the graph by subtracting 1 from your degree. Find and plot the y-intercept by putting 0 in for x. Find the zeros, the x-intercepts, by setting the polynomial equal to 0 and solving. Determine your multiplicities of zeros. Join the points together in a smooth curve, touching or crossing zeros depending upon the multiplicity and using left and right-hand behavior as a guide. So let's graph f of x equals x squared, x minus 3, x plus 4. Determine left and right-hand behavior by looking at the highest power of x and the sign of that term. Multiply out the highest power would be x to the fourth. So that means both of it'll be going up. Determine the maximum number of terms in the graph by subtracting 1 from the degree. Degree is 4, so maximum number of terms is 3. Find and plot the y-intercept by putting in zeros for x. Our y-intercept is 0. Find the zeros, x-intercepts, by setting the polynomial equal to 0 and solving. Zeros are 0, 3, and negative 4. What are our multiplicities? Determine the multiplicities of the 0. What are they? 0 has a multiplicity of 2, so it must touch. 3 has a multiplicity of 1, so it crosses. And negative 4 has a multiplicity of 1. Join the points together in a smooth curve, touching or crossing zeros depending upon the multiplicity, and use the left and right hand behavior as a guide. Okay, here is the actual graph. We did pretty good. If you wanted to be more accurate on how low to go before turning, we could have plugged in an x value somewhere between the zeros and found y value. We're not going to be picky about this, though, since there is a great method in calculus for finding the maxima and the minima. What if we thought backwards? Given zeros in the degree, can you come up with a polynomial? Find a polynomial of degree 3 that has the zeros negative 1, 2, and 3. What would the function look like in the factored form to have the zeros given above? You would place the opposite numbers in parentheses with x. So that way they would look like this: x plus 1, x minus 2, x minus 3. Multiply this out to get a polynomial. FOIL 2 of them, then multiply by the third one. And you would find that you would have f of x equals x cubed minus 4x squared plus x plus 6. Thank you for participating. The end.